answer engine. We discuss in depth the Wolfram Physics Project, Stephen's grand, indeed radical vision of a new kind of science, the title of his well-known book, in which computation via simple rules is the foundation of physical reality. The Wolfram Physics Project is a closer to truth multi-part series. We'll begin with an overview and backstory. Welcome, Stephen. It's great to see you again. It's really been too long.
Nice to see you too.
All right, let's start with an overview of the Wolfram Physics Project, your big vision, and then we'll get into the historical development of it.
The goal of the physics project is to figure out how the universe is put together, to figure out kind of the machine code of the universe. And I think we made a lot of progress in that. And I think the thing we've realized is physics is really computational all the way down. And we think we've kind of gotten to the bottom of what's there. And what's really at the bottom is this thing we call the Rouliad. And it's a very interesting story of kind of mixing science and philosophy and technical kinds of things to get us to where we are.
So let's go to the historical development. And I think you've said this is like a 50-year project, and I appreciate what 50-year projects are. Um, so how did it begin? I know you're a physicist, very young age, published papers, and then began to get into computation.
Well, let's see. I grew up in England, 1960s, excited about the future and space and all those kinds of things. After, a period of time when kind of every deep spacecraft felt like a personal friend, I thought, I want to understand the foundations of this. That got me by the age of, I don't know, 11 or so, interested in physics, discovered this remarkable fact that you could just read books and learn stuff. Didn't really matter what you were supposed to be learning in school. You could just learn as fast as you want. I also kind of had this idea that one could figure stuff out, that there were exercises in books, but people had done those lots of times before. And I was more interested in just answering questions that I came up with that might or might not have been answered before. I didn't really think about the fact that they might not have been answered before, but I just thought they were interesting questions and I was going to study them. This was by then, early 1970s. It was a time when particle physics was kind of having a golden age, quantum field theory, QCD, these kinds of things, new particles discovered. It was an exciting time in that field. And as a 14-year-old or something, I kind of jumped into doing research in that area, started publishing papers about those kinds of things. And somewhere along the way, I got interested in or involved with computers. Actually, the origin story of my interest in computers had to do with a physics textbook that I got when I was 12 years old. That was a book about statistical physics, about kind of what happens when you put large numbers of things like molecules together. What do they do? And the most sort of notable phenomenon is the second law of thermodynamics, law of entropy increase, the tendency of systems to get sort of more random over time. And there's this cover of a particular textbook that showed this sort of simulation of things like idealized gas molecules that started in kind of an organized configuration and then gradually got more disordered. And I thought, I'm going to simulate that on a computer. I had access to a very primitive computer that had 24 kilobytes of memory. It was the size of a desk and was programmed with paper tape and so on. But I thought, I'm going to simulate this particular thing from this book. I didn't succeed in doing that. Many, many years later, I discovered that the cover of that book was kind of a fake. And actually, had I been had I understood more, I would have realized that what I actually managed to simulate was more interesting than what was on the cover of the book. But I didn't understand it at the time. But then I got in doing physics. One of the features is you have to do lots of kind of mathematical calculations. I always thought that was very tedious. And I thought computers should be able to do this. So I started using computers to do sort of algebraic computation. And pretty soon I kind of had this secret weapon that allowed me to produce all sorts of results in physics that seemed very impressive. I honestly didn't understand why other physics-oriented people weren't using the tools one could make with computers. For some reason, they just were like, the programming is delegated to somebody else. I'm not going to use these tools myself. But that led me, I got interested also in cosmology, and I kind of was by 1977, 1978, was working, I was 17, 18 years old, I was working on on sort of the boundary between particle physics and cosmology, which later became a very big thing. At the time, it wasn't really yet a thing. And But that kind of again was sort of a where do things foundationally come from, either in particle physics or in the universe as a whole. Then I went from England, went to the US, got my PhD at Caltech just after I turned 20. So I was fortunate enough to get through kind of the education process pretty quickly, quickly enough that I didn't become too impatient with it, so to speak. Um, and then I got my PhD, and I was kind of like, okay, let me make some kind of plan for what to sort of do next. And I wanted to study a bunch of things in physics. I wanted to, and I wanted to have sort of the right tools to do that. And so I ended up starting to build a big computer system. This is November of 1979. I kind of embarked on building what became my first big computer system called SMP, Symbolic Manipulation Program, that was sort of a thing for doing the kinds of calculations that I thought I wanted to do in physics and other places. So that got more or less finished by 1981. I had the sort of problem that I developed a piece of technology that was really pretty useful and valuable, and that led me to start my first company. And the entanglement of that with the university, I was at Caltech still at that time, kind of got me. It was sort of a frustrating time, and I was like, I'm going to do something more interesting and fun. And I'd long been interested in the question of sort of how does complexity arise in the universe, in the world? How do we get sort of the elaborate structures of galaxies or fluid flow or biology or whatever else? And my initial thought was, I know all this stuff about mathematical physics and so on. It's very sophisticated. These everyday questions like why do snowflakes make the patterns they do, I'm just going to be able to answer those with all these sophisticated methods I know. Well, it didn't work at all. So then this was probably 1981 or so. I thought, what's plan B? Given that these sophisticated mathematical physics methods don't work, how should I think about making models for these kinds of systems in nature that show complex behavior? And that got me into the idea of, well, if I'm going to make a model, I should have some definite rules by which the system operates. What should those rules be? And because I had been involved in building this computer system, I had, well, I should explain another point about that computer system is quite relevant to the sort of the arc of what happened, is in building that system, what I had done was to take sort of an idea from doing physics and apply it to computing. And in physics, sort of the notion is we take the world as it is and we try and drill down and find sort of the primitive atomic elements from which the world is made. So when I got to build my first big computer system, computer language, I tried to do the same thing. I tried to sort of drill down and say, what are the sort of fundamental elements of computation that one can use to build up the system? And that led me back to kind of ideas in mathematical logic from the early part of the 20th century and so on. And that led me to kind of this kind of rather innovative structure for this computer language, which turns out to be the same innovative structure that I've continued using for the next 45 years, so to speak. But what was important about that was I had the experience from building that computer system of kind of starting from underlying primitives and building up to the thing one was going to get. And that was kind of the idea that I ended up sort of reusing in thinking about building up from simple programs to the kinds of things one might get in the natural world and so on.
Was there a moment of an aha experience in this process where you realized that what you were doing on a micro level could have these bigger implications on a universal level?
Yeah, I mean, when I first started running simple programs to find out what they did, I had all kinds of guesses about what would happen, mostly along the lines of if the program is simple enough, the thing it will do will be correspondingly simple. It was very clear very quickly that that wasn't the case. It took me a couple of years to really get the full aha moment. I had seen signs of it. I even had printouts of what should have been the aha moment, but I didn't understand the significance of them until about June 1st, 1984 was probably
Okay.
a key moment because I had this thing, I call it Rule 30. We'll probably talk about it some more later. It's an example of where very simple rule, very simple computational rule produces very complicated behavior. And I kind of at that moment sort of started thinking, look, this is the basic secret that nature uses to make complicated stuff. And it's something that is is at odds with the intuition that I had had, the intuition one has generally had in science, and that was kind of the launch moment. Yes, you can really have these very simple computational rules that do these very complicated things that are kind of like nature, and that was I developed that a bunch in the 1980s. Then I ended up starting to build my I started to build up that as a sort of field of science, complexity theory or whatever. And my kind of plan A was this is really cool science. I'll get lots of other people to work on this, and I'll do just my corner of it, so to speak. Plan A went very slowly, and so I kind of by 1986 I went to kind of Plan B, which was build the best tools I can, build the best environment for myself I can, and then do the science myself because I enjoy doing the science. And so I started my what's still my current company in 1986, and we started building what was at first Mathematica, now Wolfram Language, as kind of this foundational computational system for exploring the world computationally, so to speak.
So if I hear you correctly, the motivation for your companies, which have been very successful and a great contribution for scientific technology, was motivated not by wanting to build a big company or make a lot of money, but by motivated by the tools that you needed for your own exploration.
Yeah, yeah. I'm user number one, so to speak. I'm the which is always a good way, in my view, to build companies, is to build something that you actually want to have.
Yeah.
And I'm still a daily big user of our technology, and I think that's helped drive things forward. But it was I'm also a practical enough person to realize, and I like the fact that the things we build are useful to lots of other people and have led to lots and lots of other inventions and discoveries and so on over the years. And it's also as a practical matter, if you're going to build a thing as big as I've wanted to build, you can't just do that as a one person single user product, so to speak. Um, but
So to continue the timeline, let's look at then two other critical moments. The the vision to do your book, which was published 2002, I think, A New Kind of Science, which we all have, of course, and then the origin of the Wolfram Physics Project. So those two events will give us then the total overview.
yeah, yeah. So I mean, in we released our first product as a company in 1988. The company was growing very rapidly. Um, Again, there's sort of the interwoven human story and an intellectual story. It was by 1991, the company was growing rapidly, but I had many, many more ideas for the company than the company could possibly absorb. So I thought, I'm going to go off and do the thing that I originally was building this technology for, which is a bunch of science, and I'm going to sort of throttle back on injecting more and more ideas into the company because it can't absorb ideas at this rate. So I thought I'm going to go off for a year and sort of take a pseudo sabbatical and go kind of write down what I know about kind of basing science on computation rather than on mathematical equations. Well, a year turned into 10 years because I discovered a lot more than I expected to discover. And that became my big book, A New Kind of Science, which came out in 2002. And I had kind of, for that book, I'd kind of explored some of the consequences of this notion that computation could be used as a foundation for science. I mean, it's for 300 years ago, sort of the big idea was let's use math as a foundation for science.
Sure.
And this was kind of the reason I called the book A New Kind of Science is because I was exploring a new direction beyond the direction that had been explored for the previous 300 years.
Yeah, nobody argues with the title. They may argue with aspects of the idea, but nobody argues that the
You
title
know,
is legitimate.
it's funny because when the book came out, the title was probably one of the most, thought of, seen as one of the most kind of out there aspects of the
Oh
whole
yeah.
enterprise. And then, subsequently, as I've talked to people, people say, and what is this thing? Oh, it's a new kind of science. And I'm like, yeah, that's why I called the book that. But anyway, so as part of that project, as part of building up that science, I got interested in could one use these ideas about simple programs as a foundation for fundamental physics? At first, I didn't think so. At first, it seemed like the kind of rigid structure that I'd set up for these kinds of programs I was studying was kind of at odds with what one already knew from 20th century physics, and I had the good fortune to know 20th century physics quite well. So it wasn't, I wasn't kind of let me invent this thing and I believe in my thing, but it's inconsistent with what we already know. So that was, so then I, uh, I wrote some things about fundamental physics in New Kind of Science. They were pretty sensible, but my friends, the physicists, absolutely hated them because it was that was a time 2002 was sort of the string theory was still very much the thing, and I New Kind of Science was very well received in many areas. In physics, among my friends in that community, it was like we don't need this. We've got it. We understand what's going to happen. It's going to be string theory all the way down type thing, and so I sort of thought, well, I'm going to pursue this physics stuff a bit, and then I'm like, why am I bothering? The market for this is physicists, and they don't want it. So, so I ended up spending a bunch of time developing kind of my computational ideas and the whole idea of computational language, the whole idea of sort of describing the world, sort of formalizing the world in terms of computation. Also took sort of a big philosophical idea from New Kind of Science about the sort of a lack of a distinction between the intelligent and the merely computational. And that kind of led me to build Wolfram Alpha, because I had been thinking about building sort of a system that could sort of answer questions based on the knowledge of the world ever since I was a kid. But I'd always imagined that I had to sort of solve AI in order to do that. But yet, then from my science efforts in New Kind of Science, I kind of had the the sort of conclusion that I shouldn't need to build AI to build a thing that could do what I wanted to do. And so I thought, let me take my philosophy seriously and actually do a big engineering project and build this technology. And it worked. And we released Wolfram Alpha in 2009. It's been very widely used ever since. Then, okay, so we're now getting towards the physics project, which I had continued to kind of poke away at aspects of how one might use simple programs as a way to understand physics. I'd kind of poked away at that for years, doing a little bit here and there on it. 2018, I made sort of a bit of a technical breakthrough. It wasn't that exciting. It was really more of something, a technical aspect that I'd never liked in the way that I'd set up kind of the way I imagined physics might work. And then every year for the last, I don't know, 23 years or something, we've been doing a summer school for talented folk from around the world. In 2018, a couple of young physicists were there, and I was telling them about this sort of technical breakthrough I made, and they were like, "You have got to develop this. It's irresponsible not to develop this and see whether you can really sort of crack this idea of a computational foundation for physics." And then I'm getting ancient, so it was my 60th birthday, and I was like, I've been thinking about doing, this kind of thing in physics for years. If I'm ever going to do it, I got to actually go do it. So I am, with these couple of young physicists, kind of launched into this in the fall of 2019, and I thought it would take 50 years to get to a certain point in making progress on understanding fundamental physics. It didn't. It went incredibly fast. It was one of these things where it seemed like once one had a bunch of ideas, sort of had a new way of thinking about things, one could figure out a lot of things that had been very mysterious for a very long time very quickly. And so it then we were just ready to kind of tell the world about this in March of 2020, when the world kind of closed down for the pandemic. And actually, that wasn't such a bad thing, because we ended up doing, live streamed kind of science discussions and so on right in the middle of the pandemic. And I think a lot of people, by the time there are thousands of people watching in real time, some very technical discussion about physics, either that's sort of an exciting thing for physics, or the world is really bored at that moment. Um, but
Well, that was a time that Closer to Truth had a gigantic spike in its viewership. So we were both experiencing, we were both unhappy with the pandemic, but quietly we were maybe a little bit pleased on how it affected us. Stephen, this has been great. We have many more videos in this series to go. It's good to get the overarching understanding and the history. Viewers can watch dozens of TV episodes on fundamental physics and cosmology on the Closer to Truth website and YouTube channel. We feature many leaders in the field, including, of course, Stephen Wolfram. And you can watch all the videos in Closer to Truth's The Wolfram Physics Project right here. Thanks for joining us. Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing. Closer to Truth is now accepting your tax-exempt donations. Please come to closertotruth.com/donate. Thank you very much for supporting us, and thanks for watching.
Einstein once wrote an introduction to a book on astronomy. He mentioned this idea, he called it an idea of pure genius.
This is Terence Tao, one of the world's most renowned mathematicians. What he's referencing right now is how Kepler deduced the shape of Earth's orbit, which was astoundingly more clever than I had realized, but I'm getting a little ahead of myself. A lot of math enthusiasts will be familiar with Tao as a story of prodigy turned prodigious mathematician, but one of the most remarkable features of his career is how collaborative it's been, spanning an unusually wide breadth of topics within math. I had the chance to sit down with him, and I asked if there were any topics that he believed would benefit from some strongly visual presentation, and I fully expected an answer from pure math, but I was pleasantly surprised when he proposed instead a story of cosmic distances. It's the story of how humanity first figured out the sizes of objects from the size of the Earth to that of the solar system on up to the universe, and how each measurement unlocks a path to the next one.
I always liked astronomy as a child, just found like red dwarfs and neutron stars and so forth fascinating, Yeah. And I had a little telescope. As a kid, I just read all these books and said, the distance to Mars is 18 million miles or whatever, and I just sort of accepted, they figured out some way to do this. I never knew how they did it.
Science communication at its best is, to me, less about presenting facts in a memorable way, and more about showing how it is that we know what we know. When it comes to cosmic distances, it's very easy to be awestruck by the sheer unfathomable scales involved. But what deserves just as much awe, and is much less commonly highlighted in pop science documentaries, is how clever the reasoning can be at each step.
And I realized, it was always some mathematical trick. And it was always a cool trick. Like if you want to measure the distance to x, you can never just look at x. You have to look at y and how x impacts y. So the idea is clever, and then you have to have data, which needs technology and so forth. But then it's just mathematics.
In this video, we'll cover the steps of the ladder up to the planets, that moment of sheer genius that Kepler brought. And in the next part, we'll continue on up to the most distant galaxies. The very first measurement of the ladder is the radius of the Earth, a somewhat classic tale. But to even ask this question presumes that the Earth is a sphere, or at least roughly spherical, so you might wonder how the ancients first deduced the shape of the Earth.
The first really convincing proof came from the moon. And this is the constant theme in the distance ladder. If you want to measure one object, in this case the Earth, you have to use a reference object that is some distance away. See, the thing is that we're stuck on the Earth. Okay, like if we could step away, if you look from many different angles, you could see that it's round. If you only saw it from one angle, it could be a flat disk. Flat disk, if you look at it from a different angle, it would look like an ellipse. But you can actually prove, there's a nice little geometric argument actually, that if there's a convex body and every single projection is a circle, then it has to be a sphere.
I'm going to guess that most of you find this pretty intuitive. After all, if every shadow of a given shape is a circle, what could that shape be other than a sphere? But of course, a mathematician always keeps a keen eye out for those strange counterintuitive exceptions. And he shared with me a nice proof of this fact after the interview, which I'll link to in the description.
In 2 dimensions, what I just said is not true. So there are 2-dimensional shapes which every projection is an interval of the same length, but they're not round. Okay? But in 3D, there's enough perspective, as it turns out. If you could look at the Earth and you could always see that it was round, that tells you the Earth is a sphere. NASA can do this, okay, but Aristotle could do this. And he used the moon because he knew about lunar eclipses. Lunar eclipses happen when the moon falls onto the Earth's shadow. And the Earth's shadow, as you can just visibly see, it's always a circular arc. So there's a picture I can show you. This is not my photo, but someone took several images of the moon entering and exiting the lunar eclipse and it composited them together into a single shot. You can see the shadow of the Earth. This is visible proof that the Earth is round. And you don't need telescopes, sextants, spacecraft